ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
We were discussing the constitutive equations, and we had discussed quite a bit about what is hyperelastic material, the philosophy behind it. The next two classes will quickly summarize the equations which are necessary for us to go forward to look at the finite element implementation of the hyperelastic case. As I told you right in the beginning, that I may not be deriving all the equations. Maybe this class I will derive a few of them. So maybe next class I may not derive the equations. I'm going to give you the final versions of it, so that we will use that for our finite element work later. So let us look at some specific things in hyperelasticity. In fact, if you look at the materials that come under, or that can be classified under hyperelastic materials, they can be classified as, of course, isotropic and anisotropic. I'm not going to cover the anisotropic part in this course, because that's again a huge area. You need to know a lot more of continuum mechanics in order to cover anisotropic part of it. Maybe towards the end, if there is time, I'll indicate how we approach the anisotropic problem. But the applications of anisotropic hyperelasticity is not very high, except biological materials. You really do not use anisotropic hyperelasticity to that extent. In fact, I'll just comment on that in a minute. Let me complete this, the other classification. The other one is, of course, isotropic hyperelastic materials. The other type of classification comes from whether the material is compressible or incompressible. So you'll say that incompressible and compressible. So essentially what we are going to do now is that for hyperelastic material which undergoes, say, isotropic incompressible, we are going to put down some equations, okay, in terms of general size, that is general strain energy function, and then we will go to specific strain energy function and state some of them. So essentially what I am going to cover is isotropic incompressible, which has the maximum amount of, I would say, application. So isotropic incompressible hyperelasticity. For sake of completion also, I'm going to state the isotropic compressible hyperelasticity. I'm not going to the details, but I'll also complete in the next class what is called as isotropic compressible hyperelasticity. What I'm not going to cover, okay, though I may state one or two sentences, is the anisotropic incompressible hyperelasticity and anisotropic compressible hyperelasticity. Or in other words, anisotropic hyperelasticity I am not going to deal with in this course. Now, let's just, before we go further, because we made this assumption, let's just check what this anisotropy is physically, what it means, and why we can, for many problems, we can do away with anisotropy and use isotropic materials. For many practical problems, for example, if you take, say, tires, tires is basically, I talked about hyperelasticity. Most of them are incompressible hyperelastic materials. And of course, you can also classify another category of materials called isotropic nearly incompressible materials also. But usually do not put down a separate constitutive equation for it, but you can also say that there are some materials which are nearly incompressible. But many times we treat, okay, because of the finite element formulations, we treat incompressible materials to be nearly incompressible and so on. That we will discuss when we come to the finite element part after 2 classes. But what I want to specify is that, say for example, if you take a tire, then there are reinforcements running, okay, that makes the material composite, or that makes, in a gross sense, the behavior to be anisotropic. Okay. In other words, here are reinforcements which can be identified. Say that this is the steel reinforcement which can be identified, okay, and then you look at its behavior, okay, along with the rubber matrix. If this is the case, then you do not write down separately, or you do not classify this as anisotropic on a micro scale. So what you usually do is to write down isotropic behavior, isotropic constitutive equation for the matrix material, and then take that reinforcement separately and usually put special elements which are called as reinforcement elements or rebar elements, or in other words, you treat them as two different materials, and there are ways of handling them, okay, in finite element analysis. On the other hand, you have biological materials where there are collagen fibers, okay, tens of thousands and millions of them. Okay, if you take a piece, there will be so many of them. You cannot one by one pull up and say that, yeah, this is the collagen fiber, this is the fiber that's running, and this is the other fiber. So I will put one special element for this fiber, another for this fiber, and so on. In other words, it is so very intermingled at a scale, at a much lower scale, that it will not be very easy to separate them out and treat them as a separate material and say that I have a base material which behaves in an isotropic fashion, and on top of it I have material which makes it to behave anisotropic. I can't say that. So take a piece, the whole piece behaves as an anisotropic, material. Okay, there's always a problem with that anisotropic, and when I say anisotropic, it looks as if it is anisotropic. So I said an anisotropic material, right? So in this case, if I have collagen fibers that are running and I take a biological specimens, I want to treat it using finite element analysis, I have to necessarily treat them as anisotropic material. Now I'll also indicate one or two other things with the anisotropic material, but the major good thing is that the procedure that I'm going to put forward now is exactly the same for anisotropic. Just that we do not have enough time to complete this whole anisotropic material behavior. It's only that, but the procedure is exactly the same. So that way, if you want to go back and read a paper, it will not be any way different. I'll also indicate what they are in a minute. One of the most important theorems that we're going to look at is what is called as representation theorem. Representation theorem, or sometimes people call this as representation theorem of invariance. What it means is very simple. What it means is that if you have a scalar valued tensor function, nothing great, or strain energy, scalar value, okay, tensor function, which means that it's a function of tensors, say C, such that it is not affected by rotations, or in other words, if it is isotropic, it is isotropic, then this function can be written in terms of the invariance of the tensor valued function. Though the proof is very complex, quite involved, I am not going to prove this, but it is very simple to understand. So what it means is that for isotropic materials, now how do I express when I say C, and how do I express this as isotropic materials? Remember, yesterday we wrote, or last class we wrote that this, if I have to have this to be an isotropic material, then this has to be written as, or this is equal to f of q transpose. We already said that the strain energy function can also be written in terms of C and E because they are all functions of, say, U and so on. So suppose I write this as C, let's see in a minute, tell me how this should behave, this function should behave if it were to be an isotropic material. What is C? No, what is C in terms of, yes, yeah, F transpose F. So just check how this should be. Note that F varies as, or if I just for a minute call that as F star, so F is equal to FQ transpose. So write Cauchy tensor, or in other words, that is F transpose F. So this should be in terms of star, how it should be, the start coordinate. So substitute from here, you will get that has to be QC Q transpose. Just verify that. So if you can have, or if you have a strain energy function like this with this equation, then the representation theorem states that such an equation can be written in terms of the invariance of this tensors. What are these invariants, by the way? Yes, they are different for different things. Say I1 is equal to the invariance of C, and so if you can, if you want to express this, say in terms of lambdas, which are the principal values, or lambda squared, which are the principal values of C, then you can express them as I1 as lambda 1 squared plus lambda 2 squared plus lambda 3 squared. Lambda squares are the eigenvalues. And then I2 rather can be expressed as lambda 1 squared, lambda 2 squared, lambda 2 squared, lambda 3 squared, plus lambda 3 squared, lambda 1 squared. And 3 is equal to the determinant of that, so it's equal to of this diagonal matrix, and that is equal to lambda 1 squared, lambda 2 squared, lambda 3 squared. Some of the textbooks like Wood expresses this as lambda 1 power 4 plus lambda 2 power 4 plus lambda 3 power 4. So if you see this in a different form, don't worry about it. That's another form of writing the second invariant. Yeah, it won't be different because that can also be shown to be an invariant. Okay, you have to know some invariant theory to say that. Okay, it can also be written like this. No. See, invariant. What are invariants? Yeah, this will not change with the coordinates. Okay, so you can also show that if you write this in terms of lambda 1 power 4 lambda plus lambda 2 power 4 plus lambda 3 power 4. Okay, they also can be formed as an invariant. Just as a caution, I'm just telling you, if you see different things, don't worry about it. Okay, that's another way of writing the second invariant. First and third invariants are usually what I've written here, they are the same. So that theorem gives us a lot of advantage, okay, of writing down the stress-strain relationship. So there are two ways in which you can write down the relationship. One is straight away in terms of invariance. Of course, if I do not If I do not want to write it in terms of lambda 1 squared, I have to, for this is one way of writing it, simple to write. But of course, if this is not given, you can also write in terms of C itself, I1, I2, and I3. And how do I write that? This is trace of C. So this is one way of writing it, but that's also equal to, I'm going to use that later, trace of C, and this is equal to half of trace of C squared minus trace of C square of C. That's I2, and I3 becomes a determinant of C. Okay, these are the three ways in which it can be written. And now my procedure is very straightforward as to so what is my goal? And my goal is just to express. So I've come one step down, saying that this strain energy function, which is a function of C, can now be expressed in terms of this invariance. That's the one step which I've come towards writing down the relationship between deformation and the stress for an isotropic material. Right, what is the next step? Next step is just to substitute this into my expression which I had given you in the last class. What is the expression that we saw in the last class? P, say for example, if you look at S or if you look at P, okay, then we had written that in terms of dou psi by dou C. So in other words, if I remember right, we had written that as 2 into dou psi by dou C. Okay, right? And note, of course, one of the important things which I may not continue with that line again. So this is in the reference configuration. This equation is written in the reference configuration. Since the eigenvalues happen to be the same, whether I use C or whether I use B, this whole equation can again be written in terms of B as well. That is where F is in the left of F transpose. Okay, that is in the spatial coordinate. So I can write this down, say, as like that as well. Either way I can write it, either in terms of C or I can write that in terms of P as well. Okay. So my job becomes very simple, because now that I know how to write this for S, so what I need is only that quantity. In fact, you will see that what all we expand after this is only algebra. Only one more concept is there. Okay, after this it is algebra. Okay, so let us see. So that's why I said I'm not going to derive all the equations. Let's see how we write this. Okay, this strange function psi with respect to differential with respect to C. Very simple. How do I write it? Oh. Chain rule or chain rule. That's all. Dou psi by dou IA, dou IA, dou C. In other words, dou psi by dou I1 by dou C plus I2 plus I3. Right. So let's keep this, because this is what will vary from one material to another material. This function is one which is going to vary, or in other words, this function here, what we have put here, is going to vary from one material to another material. Okay, so or one type of material to another type of material. Okay, let's keep that as it is. But let us now look at a general formulation or general equation. From there we can quickly reduce it to different forms. In fact, that also I'm going to reduce it in a minute. So what is the general equation which everyone writes? Simple. I need to know, what are the things I need to know? I need to know dou I1 by dou C, dou I2 by dou C, and dou I3 by dou C. If I know all these things, that is dou I1 by dou C, I2, and I can get first one expression for S. No problem at all. Substitute it here. Now if I know this function, I can get straight away the relationship. Let's see what they are. Let us say what is dou I1 by dou C. Have a look at this. Anyway, I'm going to write the results. Maybe I'll give you a couple of minutes, at least the easier part of it. Let's check whether you're able to do it. First two. Third one I will derive it. It's slightly more involved, and that's a very important relationship. Okay, so I will derive that. That derivation is quite, it's not very straightforward. So I will just derive that part alone, but the rest of it, let us see whether you're able to do. That is dou by dou C of det C, okay, determinant of C, is the only expression which requires some amount of manipulation. So let's write down these two. So dou I1 by dou C is equal to what? Fantastic. So that is I, basically because trace of C, that means C11 plus C22 plus C33. Okay, that's what you will get for trace of C. So dou I1 dou C of say AB is equal to delta AB. So in other words, what it means is dou I1 by dou C11 is delta 11, which is equal to 1, and so on. So obviously, it's an excellent answer that this is going to be I. Let's see how you do dou I2 by dou C. Have a look at this here and see whether you'll be able to do that. So chain rule, don't forget the chain rule. So first term is what? 2 into trace of C into, so first term is half 2 into trace of C. Is it C? Then dou of trace of C by dou C, which is I, minus, simple, dou of, yeah, 2C, dou of trace of C squared, okay, which is equal to 2C. So that is the first part of it. And now, most important thing, how do I get, and this of course can be written in a slightly different fashion. Trace of Ci can be written as, so I1, this is I1, I minus 2C or minus C. The most important thing is, hey, is that correct? 1 minute. Trace 2 times trace of C, yes, into dou trace of, yeah, that's correct. So C squared 2 of, to trace of C squared, dou by dou C squared, no, yeah, C is there, correct. Okay, so and lastly, dou I3 by dou C, that is dou by dou C of determinant C. What is that expression? How do we get this? Dou of any quantity. So dou of dou A, say determinant of A. It's actually equal to, the result is determinant of A A inverse transpose. Now to start with, this is a very standard procedure actually. Let's say determinant of A plus dA can be written as determinant of A into I plus A inverse dA. Which can be written as determinant of A into determinant of AB is equal to determinant of A into determinant of B. So determinant of A into determinant of I plus A inverse dA. Right. Now what is this? Let us take that second term, determinant of, let's take determinant of I plus A inverse dA. Does it ring a bell? This is very similar to the determinant which we use for the characteristic equation as an eigenvalue problem. What is that? A determinant of, say, if I want to write down the characteristic equation for A, how do I write down? Determinant of A minus lambda I. Yes, compare that and this and say what is the lambda. Say, for example, this can be looked at as if lambda is equal to, okay, if you want you can write that down as determinant of A inverse dA minus of minus 1 I. Compare these two now. So this is the characteristic equation for A inverse dA. Small jugglery. You will see most of the derivations are like this because you want a result, a very nice result. So usually what you do is this kind of small mathematical jugglery is what you will be doing, nothing else. Okay. Now having done that, what is my next step? Write this down in terms of the polynomial expression that you usually do. How do you write this down in a polynomial expression? Usual, in terms of invariance, usual expression that you write down will be, say, lambda cube minus I1 lambda squared plus I2 lambda plus I3 is equal to 0. This is how you would write it. So if instead of that you just write this down as, so let's say how you will write it down. Substitute for lambda and then simple, you will get 1 plus the first invariant of A inverse dA. I'm just changing the notation slightly because I2, if I write 2 here you will get confused. So I'm just saying that it is 2 A inverse of dA plus 3 A inverse of dA, where I substituted into my expression of lambda cube minus I1 lambda squared plus, no, yeah, minus 1. So lambda, everything will be minus. Okay, so lambda cubed, when I substitute, that becomes minus. So everything will be minus. So we can write that down as something like this. This is the characteristic equation which you can write it down. Right? Now, what is this? This is 1 plus trace of A inverse dA plus the second and the third invariants have higher order terms of dA, okay, squared terms of dA. And so I am going to because this determinant is very close to dA. So I'm going to remove that. So I'm going to say that these are order of dA. So substituting this into this expression here, you can write that down as determinant of A into this expression, okay, 1 plus, or in other words, you can say determinant of A plus determinant of A trace of A inverse dA, okay, and we'll stop with that. Because other terms are d squared terms, so we can neglect it. In other words, we are linearizing it. So in other words, it brings out another equation. Of course, this determinant of A trace of A inverse dA can also be written as, because alpha of determinant of A is equal to determinant of alpha A, so we can write this down as a trace of, alpha of trace of A is equal to trace of alpha A. So you can say determinant, this will become determinant A inverse dA. Okay. Now that's the first thing. Since I have normalized it, I can also express the determinant of A plus dA in terms of the Taylor series expansion. Let us see how we do the Taylor series expansion. Now what I'm going to do is simple. Let's see how many of you do it. I'll give you 2 minutes. Write this down in Taylor series expansion. Okay, determinant of A plus dA. Compare the second term of the Taylor series expansion with this, and you get the answer. That's all. So the procedure is very simple. Then the next step is to write this down in terms of Taylor series expansion. Write it down. Suppose I have phi of A plus dA. How do I write that down? Suppose I have some function phi is equal to phi of A plus dou phi by dou A dA plus higher order terms. Okay, here instead of this phi, what is that you have? Determinant of C, or determinant of A. So this will be dit A dA. Now let's see, compare this and that. Yeah, dou of simple, this becomes, actually this becomes determinant of A. Compare this expression with this expression, what we have here. So the second expression is what we are interested in. So dou of dou A determinant of A is equal to trace of what? Determinant of A inverse dA. Determinant of A inverse dA. Right?
That is transpose. Dou by dou A get transpose.
No, I have not yet come to that. There is no, dA. Right? Yeah. Sorry, this I left out, so just I've added that. But what is this? This is nothing but how I want to write it as a double contraction or double dot product. So this becomes determinant of A inverse transpose, noting that determinant of A is equal to A transpose dA. Yeah, this is simple. We had done that yesterday. What is A double dot B. This is trace of A transpose B. This is equal to B double dot A, trace of B transpose A, and so on. Yesterday we had done that the last class. And so comparing the left hand side and the right hand side, very simple. If you have any difficulties, it's quite straightforward. You say that B, you can write it in terms of indical notation. Okay, A I J B J I, okay, or A I J B I J. Then you can go and look at the trace of this. You will see that they are the same. So comparing the left hand side and the right hand side, you will see that dou by dou A of determinant of A, which we are interested in, is determinant of A inverse transpose. So that's the expression we have been looking at. Okay, substitute that, or in other words, A is replaced by C, and that is what you get. So dou of dou C, determinant of C, is equal to determinant of C, C inverse, and determinant of C is nothing but I3, so I3 C inverse. We have removed many of those things in order to derive this. Go and substitute that back. Now go back and substitute all these things into my expression for S and tell me what that expression is. So that is the fundamental expression. That's why I'm taking time to derive it. Go back and substitute. You have all those things before. Go back and substitute and say what that S should be. Okay, remember that we had written down this as 2 into, sorry, this is how we had written it down. So this will now become, let me write down, let me substitute for all that things which we did, 2 into dou psi by dou I1 plus I1 dou psi by dou I2 into I1, into I minus dou psi by dou I2 C. What I'm essentially doing is to resubstitute back what all I did, okay, plus I3 dou psi by dou I3 C inverse is my final expression. So this is the relationship. So once I give this, you will be able to find out yes. You can also write this in terms of sigma. Please write that down. So in terms of sigma, sigma is equal to J inverse F S F transpose J inverse F S F transpose. Substitute that back. You can write the expression for sigma to be 2 J inverse multiplied by or pre-multiplied by F, post-multiplied by F transpose. You will get that to be I3. Do that. I'm not, as I told you, I'm not going to derive all these things. Dou psi by dou I3 I. It's a very important expression. Dou psi by dou I1 plus I1 dou psi by dou I2 into, if you want to express this in terms of B straight away instead of C, it's more appropriate. So you can write this as B minus dou psi by dou I2 B squared. Note note this carefully, that we have got this expression from here, which means that the size, these free energies are still in terms of C. They are still in terms of C, though we have written here B, okay, they are in terms of C. We can also write down sigma if psi happens to be written as the free energy function happens to be written in terms of B as well. You can write that down also. If that is the case, in fact, you can write down sigma to be 2J inverse dou B B. One of the beauty of this is that you will see that this expression commute same way, this expression, that you can verify this, that also commutes. You can verify this, please verify it. So that also commutes. So we have now grand expressions for S and sigma. Now all other expressions that we are going to use actually come from this. They are simplifications of this expression. So what is the assumption that we have made? What we have made is that the material is isotropic. Material is isotropic. Having made that assumption, we get this. From here you can follow through for incompressibility, compressibility, and so on. Now it's usually customary to write down not this free energy function not in terms of I1, but in terms of lambda 1, lambda 2, and lambda 3. So you can write down, in fact, this in terms of lambda 1, lambda 2, and lambda 3. That's the usual way of writing down this expression. Okay, so that I'm not going to derive this, and again it's a big derivation. We can write down PA, the principal stress of, or in other words, the corresponding pure law Kirchhoff stress. A varies from 1 to 3 to be dou psi by dou lambda A, often used expression. SA, which is the second pure law Kirchhoff stress, is written as 1 by lambda A dou psi by dou lambda A, and sigma J inverse lambda A So these are the expressions in terms of the principal stretch values. Now, so in other words, when I express these strain energy functions in terms of principal stretch values, which I did yesterday, for example, for Ogden model, what we did was to express these things. Remember that sigma of alpha p by mu p lambda power alpha p and so on. We had expressed that in terms of an expression. So lambda A, lambda 1, lambda 2, and lambda 3. And if you remember that we had used for Neo-Okean and for the Yost model in terms of I's, I1, okay, and I2. Remember that we had used that as well. Now, note that one more small thing which you can see, that when f is equal to 1, that in other words, it is necessary that when there is no deformation, lambdas are what? 1, 1. So I1 becomes 3, I2 becomes, I2 becomes 3, okay, and I3 becomes 1. Right. So with this background, let us now move over to what we call as the incompressible hyperelasticity. Incompressible hyperelasticity. What do we mean by incompressible hyperelasticity? What is the condition that I have to? Very good. So determinant not 0. So we said that it can't be. Yeah, we had put down important conditions. The determinant of j is equal to 1. Okay. So we have to also install or implement that condition. Okay, to the, or in other words, I should have that to consist of two terms to take care of the incompressibility as well. Okay, and the second term would be in terms of p into j minus 1. Okay, we will talk more about that in the next class. So we are now moving to incompressible hyperelasticity, which will have two functions. Okay. Fine. We will stop here. It's a nice time, good time to stop, because we will start incompressible hyperelasticity in the next class. Is there any questions on what we have done? We will answer that and then close this. Please revise whatever we have done. We'll stop here. We'll continue in the next class.